Hi everyone, Professor Bob Young here. In this instructional video, we're going to look at complex numbers in polar form and the famous Abraham-DeMoivre's theorem. All right, now many of you remember from your algebra experiences, pre-calculus algebra, college algebra, etc. Complex numbers in standard form were in the form a plus bi, where the a part of the complex number was called the real part. So we'll put real number part here is the a part. And the bi is called the imaginary part of the complex number, a plus bi. And remember, the complex number I was developed by the French mathematician René Descartes. And he was telling his French buddies back when that, I do not like the fact that you can't take the square root of a negative number. So he created his own number system where he called the square root of -1 the imaginary number I. And that discovery, believe it or not, led to electricity today. And it has a lot of electronics applications, electrical engineers, and so forth deal with I's quite a bit. And if you square both sides of this equation, remember I square is actually the number -1. All right, so getting back to how Descartes wanted us to write these things, let's just take a few examples of these complex numbers in standard form and we'll refresh. Let's put 5 plus 3i. Let's put -4 minus I. We can also put -5 1/7 plus 3i, because I know y'all love fractions and so forth. So I'm just making up some complex numbers here in standard form. And notice a lot of students have the misconception that a and b must always be positive numbers. Not true, all right? A, notice, can be positive or negative, as can b be in these cases. And let's just put one more in here for good measure. Let's put 2 minus 6.1i. All right, so I tried to throw some fractions and decimals and so forth in there. Now, next, we are going to learn to graph on what is called the complex plane. All right, so we are now going to go from the rectangular plane to the complex plane, where the x-axis is going to be called not the x-axis anymore, but the real number axis or real axis. The y-axis is going to be called the imaginary axis or the I-axis. All right, so if we want to come over here and plot a few of these points, let's take 5 plus 3i. If we wanted to graph that in the complex plane, you would just go over 5 on the real, up 3 on the imaginary, and there is your first point. And if you want to, we can call this point A, this point B, C, and we'll just go ahead and label them like this. Okay, so that way we can go back and forth. All right, so this is point A. And in the homework, they'll actually have you just go ahead and get familiar with the complex plane and graph a few things here and there. Let's graph another point here, -4 minus I. It's almost like plotting points in the rectangular system, would be point B here. All right, C, -5 1/7 would be a little bit past 5 and then up 3 here. So I'll try to get real tight in here. Close enough for government work. -5 1/7 3. And let's do point D here. I'm sorry. We'll go 2 and -6.1 I would be about right there. All right, so this is just getting you familiar with graphing points in the complex plane. All right, next up in this slide, we're going to look at what's called the absolute value of a complex number. So if you have an absolute value of a complex number in standard form, or some books will call it rectangular form, a plus bi, they will say the absolute value, and they call the complex number z sometimes, equals the absolute value of a plus bi is given by the square root of the a number plus the b number, the square root of a squared plus b squared. So let's just go ahead here and we'll take a number, we'll put a point, let's take 3, we'll call this point 3 plus 5i in the first quadrant, and we will find what is called the absolute value of this number. All right, so I'll come over here on the side and say the absolute value of 3 plus 5i would equal the square root of 3 squared plus 5 squared, which should equal the square root of 9 plus 25, which would be the square root of 34. And really what this is talking about, the absolute value here, is really just the distance from the origin to that complex number. All right, because if you went ahead and dropped a perpendicular here, this would really just be the Pythagorean theorem, a squared plus b squared is c squared. So this would really be the hypotenuse that you're getting when you find the absolute value, or I'm going to call it the distance of a complex number. All right, now another thing we're going to learn in this section is what is called the polar, I've heard it called polar or trigonometric form of a complex number. All right, so we are going to change from this standard form to polar or trigonometric form, where z becomes r times the cosine of some angle theta plus I sine theta, where look at what seems to be coming back here. These things remind me of something. Great Scott, it's the Fantastic Four. It looks like A equals R cosine theta, B equals R sine theta. Now remember when we did it before, A was really what? X, and B was Y, which really kind of matches up here when you think about it. This is the A axis, this is the B or imaginary axis, and then R, we just said the radius would be the distance here we're getting. And then the tangent would be, instead of y over x, b over a. So it's very similar to some of the past videos we've looked at. Now notice in these, r is called the modulus of the complex number, and z, the angle, is called the argument. So we have some terms for each one here. So I tell you what, let's go ahead and take this 3 plus 5i, and we will write it in polar form here. All right, so I'm going to say 3 plus 5i. Now, in order to write it in polar form, we're going to have to, we already got the r number there, okay, because that is the square root of a squared plus b squared. So we can come over here and call this r if you want to. And then if we want to get the tangent of the angle, and we'll go ahead and get it in degrees first here. So I'm going to go ahead and come over here on the side and say the tangent of theta is going to equal 5 over 3. Now that's b over a, of course, here in this form. And you know how to get angle theta here. We're going to take the inverse tangent, the arc tangent, or what Young likes to call the angle getter. So let's pause real quick. Let's go into degrees. Let's get this on our calculator. All right, and I got the angle's about 59 degrees, just rounding it to the nearest degree there. All right, so now notice, now that we're going to go from a plus bi to this polar slash trigonometric form. So here's how we're going to rewrite this. We're going to say this equals r, which we found as the square root of 34, times the cosine of the angle. So we're going to say that is 59 degrees plus I sine 59 degrees. So this is what is called the polar or trigonometric form of the standard form number. All right, so when we put in the inverse tangent here, we found that this angle here was about 59 degrees. Now there's a way to check this on your calculators as well. So if you go ahead on your calculator and put the square root of 34 and multiply it by the cosine of 59, you're going to get a number very close to 3. You might get like 2.99999 or 3.00001, but it'll be very close because we rounded this. And of course, the square root of 34 times the sine of 59 will get you like 4.999 or 5.000, but it'll get you very close to the second number 5. All right, so we have now discussed lots of interesting things, and we're going to do another example with this as well. All right, so for another example, let's take the complex number -3 plus 3i, which I will go ahead and plot here in the second quadrant. And I'll go ahead, I'll put a little dotted line out here. All right, so here is the point. Now I want to go ahead and change this into polar / trigonometric form. So again, there's two things I need to get. I need to find the absolute value here. So I'm going to say the absolute value of z is going to be the square root of a square plus b square. So this is going to be the square root of 9 plus 9 is the square root of 18, which simplifies into 3 times the square root of 2. Right, the next thing we need to do to write this in the polar form or trigonometric form is to find the tangent of the angle. All right, so the tangent of the angle we are going to say is b over a equals, in this case, is going to be 3 over -3 here. So there's your a number, here's your b number. So we're going to say the tangent of theta is -1. Now when you put that in your calculator, and here's again where you need to know your unit circle, it is going to spit you out -45 degrees if you're in degree mode, or -pi/4 if you're in radian mode. So remember, the inverse tangent only exists the range from -pi/2 to pi/2, or -90 degrees to 90 degrees. So your calculator gave you this angle, but you need to know you're in which quadrant here. So you need this angle. How do you get it? Well, you're going to add 180, of course, and the angle that we need is 135 degrees. So always make sure whatever quadrant you're in, you know what angle you're getting in that quadrant. So review your quadrant 1, 2, 3, 4 angles. So now we've got everything we need to know to write this in the new form. So we're going to say the standard / rectangular form, this is going to equal 3 times the square root of 2 times the cosine of 135 degrees plus I times the sine of 135 degrees. And again, you could check this by distributing and you would get these numbers over here or very close to them. All right, now I want y'all to go ahead and plot this polar point, and I want you to change it into the polar trigonometric form based on the first few examples. So that's nice about the videos. You can stop, pause, come back. All right, so I'll give you a second, pause. Okay, if you're back, here's where you should have plotted this point. 2, -4 is down here in the fourth quadrant. And I do these on purpose because I find students in the second, third, and fourth quadrants often miss the angles and they get in trouble. All right, so we want you to go ahead and write this in polar form. Let's go ahead and do this one in radians. Okay, so we'll make the angle in radians here because they may ask you to do both degrees and radians. So once again, I'm going to find the absolute value of a plus bi, which is really that distance I have down here. And once again, I'm just going to say, well, that's pretty easy. It's going to be using the distance formula, the square root of 2 square plus -4 square, which will give me the square root of 4 plus 16 is 20, and that will simplify into 2 times the square root of 5. All right, tangent of theta equals b over a, which is negative 4 over 2, in this case negative 2. Theta would equal the inverse tangent of negative 2, and here's where you have to be careful again. Now go to radian mode here, and let's go ahead and find our answer. All right, so my calculator, once again, knowing that the range of the inverse tangents between negative pi over 2 and pi over 2 gave me negative 1.1 radians. Now again, we may want this angle here. How do you find the angle we need if we're in radians? Well, we're going to have to take this negative 1.1 and add 2 pi to it. Or you could think about going all the way around the circle as 2 pi and then subtract the 1.1 to get a radian answer. So let's do that real quick and come back. All right, so I got about 5.18 radians when I added the 2 pi to this. So writing this now in the polar form, I'll just come up here and write it right next to it here. We're going to say that this equals 2 times the square root of 5 times the cosine, if they want this in radians, of 5.18 plus I sine 5.18. All right, so that concludes another example here. All right, now the next concept we're going to work on is what's called the product rule for complex numbers, and it is on the top here. And it says if you have two complex numbers, z1 and z2, in order to multiply them together, so I've got some examples down below here, you will take the two modulus, or the r values, and multiply them together. And then on the angles, or the argument, you just simply add those together. All right, so we'll go ahead and use this rule here. Now, usually a lot of students will go, put a bunch of these on the test, Young, put tons of them on the test. So we're going to say the product of these two complex numbers, z1 times z2, is just going to take the two modulus, 4 times, oops, wrong number there. Careful, Young, 4 times 7. I don't know where I got 5 from there. All right, been doing too many videos here. Times the cosine, if you look at here, just add the two angles together, or arguments. It would just be 50 degrees plus 100 degrees here, and then plus I sine. And a lot of students will start putting dittos on this because these are always going to be the same angle here when you add them. So they'll have that look. All right, so the product of these two is simply 28 times the cosine of 150 degrees plus I sine 150 degrees. And this is left in polar / trigonometric form. Now I tell you what, on this one, let's go ahead and change this into the standard form or rectangular form. We can do that as well. So we're going to take the cosine of 150 here, and let's take its unit circle value. Hopefully everyone remembers that is going to be negative square root of 3 over 2. The sine of 150 is going to be 1/2 I. See, so we can easily multiply the 28, distribute it through both of these if we want to write this in the standard rectangular form. So we would get negative 14 times the square root of 3 plus 14i. So we can also go, and you might have some homework problems where you're taking polar form and then asked to just change it into the rectangular or standard form. All right, let's do one more example. Now I also have one in radians here, so we're just going to go ahead and take and multiply the two modulus, 3 times 4 here, so that would give us 12. I'll just go ahead and write this out, times the cosine, and this would be in radians 5 pi over 8 plus pi over 16. So again, if you look up top here, you're just multiplying the modulus, adding the arguments or angles together here. All right, so we'll come back down, plus I times the sine of those, the sum of those angles. So make sure we get this correct. And that will be that. All right, so the final answer here would be 12 times the cosine of 5 pi over 8. Now, if we change this to 16s, this would be 10 pi over 16, plus pi over 16 would be 11 pi over 16, plus I sine 11 pi over 16. All right, so this would be left in polar form. But I tell you what, I want y'all to pause your calculators and write this in rectangular form for me. Now notice this is not a unit circle angle as we know and love, and we used and got this exact answer up here. So we're going to have to approximate this one. All right, so go to radian mode and let's go ahead and let's say we'll go out to the nearest hundredth or 2 decimal places. So pause right now, come back and see if you get what I got. All right, so when I took 12 times the cosine of 11 pi over 16, I rounded it 2 decimal places to negative 6.67, and I times the sine of 11 pi over 16, I got plus 0.998 I. So these are both very interchangeable. You can go back and forth from rectangular to polar, polar to rectangular or standard form, and that's how they'll work on them. Now, of course, if there is a product rule for these polar creatures, there is what's called the quotient rule. So the next thing we're going to look at is division of complex numbers. And once again, they call each complex number Z1 and Z2, and I provided some more examples both in degrees and radians. And what you do here, think about when you multiplied them, you multiplied the modulus or the numbers, the R values in front. When you divide them, you divide them. And on the angles or arguments, when you multiplied them, you added them, but when you divide them, you simply subtract them. So again, these aren't too bad, so we'll stop and we'll go ahead and do these real quick. So the quotient of these two complex numbers would be the R values divided, so it would be 50 divided by 10, times the cosine of, just take the two angles, 80 degrees, subtract 20 degrees there, and then plus I sine, and you can put ditto. A lot of students will put ditto there. And we'll go ahead and clean this up. So the quotient of these two numbers would be 5 times the cosine of 60 degrees plus I sine 60 degrees. So this would be polar form. Now, if we wanted to go rectangular or standard, we would take the cosine of 60, which we know is 1/2, the sine of 60, which is the square root of 3 over 2 I here, and we could then distribute the 5 on the outside through and get this answer, 5 over 2 plus 5 times the square root of 3 over 2 I. All right, I want you guys to pause and see if you can do this one, and then come back, and then I will work it with you here. So take a second. All right, if we're back here, we're going to divide these two complex numbers. Z1 divided by Z2 will be 3 divided by 4. And if it's okay with y'all, when you start doing enough of these, you'll just come over here on the side of your paper and you will subtract these angles here. So pi over 5, if you get a common denominator of 10, it'll be 2 pi over 10 minus pi over 10. So you'll get 3/4 times the cosine of pi over 10, and then plus I sine pi over 10. And this would again be polar form, and if you wanted to, you could go rectangular on it as well. All right, now it is my pleasure to introduce a famous mathematician from the past, 1667 to 1754, the man known as Abraham DeMoivre. And one of his accomplishments was he made a theorem where you can take any complex number and raise it to a power and make it real easy to do. All right, now before I get to the famous DeMoivre's theorem up top here, I wanted to give y'all a little insight on how valuable this theorem is. So think about taking 4 plus 3i, a complex number in standard form, or your book calls it rectangular form, and raising it to even, let's just say, a power of 7. All right, so I'm just going to take 4 plus 3i and we'll multiply it together conventionally. We'll just take 2 of them here. Now remember, 7 of them means you would keep going another 4 more times multiplying, but we'll just take these. And when you FOIL these, remember, you're going to get 16. In this case, plus 12i would be plus 24i, and then 3i and 3i would be plus 9i squared. And then I squared is the number -1. So if you remember doing these in pre-calculus algebra and college algebra, you end up, this is just 2 of them now, 16, and that'd be a -9. So you would get 7 plus 24i. Now we would have to take this 4 plus 3i, multiply it, another 4 plus 3i, another 4 plus 3i, and keep going and going and going. Do you know how much work that would take? So this DeMoivre, and think of this number, or a 70, or a 700. I mean, forget about it. It would be impossible. All right, so looking up top here, DeMoivre came up with, and we've got z to some power n. Now remember, z is just a complex number here. And notice we've got this complex number written in polar form. So it's r times cosine theta plus I sine theta, which we've done a whole bunch of examples in this video, raised to some power of n. So what DeMoivre came up with, the famous DeMoivre's theorem, is he found out if you take this power n and put it on the r here, so r raised to the n. Okay, that's the first step. And then you take this power and multiply it by the angles in here, that it is a very quick way to multiply complex numbers raised to higher powers. All right, so we've got a few examples here. Let's take a look at these, and we'll do these. All right, so DeMoivre's rule says if you look up top, if we take the 2 on the inside here, the r number, and we raise it to the 3rd power, so we're going to execute DeMoivre's theorem here, all right? And then we're going to take and multiply that by the cosine of the angle, which in this case is 10 degrees, and then we're going to multiply that by 3, plus I sine 10 degrees multiplied by this power 3. That it is just a shortcut, a quick way to multiply complex numbers of higher power. So we'll end up in this case with 2 cubed is 8 times the cosine of 30 degrees plus I sine 30 degrees. All right, so no doubt one of these will be on the test. I mean, we have to go after this famous mathematician and be able to do things and so forth. Now again, we could change this into rectangular form, because notice here it says write the answers in both polar and rectangular form. So let's keep going. So we know the cosine of 30 degrees, square root of 3 over 2. Sine of 30 degrees, we'll put 1/2 I. So this would be 8 times the square root of 3 over 2 would be 4 times the square root of 3 plus 4i. All right, so we will just go ahead and circle these answers here. So this answer would be the polar or rectangular, the polar form, and then this would be the standard or rectangular form here. All right, so for our second example here, I put one in radians for you. We're going to go ahead and execute DeMoivre's theorem on this one, so I'll come over here on the left a little bit. So we're going to take this r value 1/2 and raise it to this power of 6 here. and then we're going to multiply the angles. We'll take the cosine of pi over 12 radians, multiply that by the power. See, so this power, if you look at it here, whatever's out here gets raised to it, and then the angles get multiplied by that. So the n is very important here. All right, so we'll come on down and put plus I sine pi over 12 times 6. And this will give us 1 over 64, I believe is 1/2 raised to the 6th power, times the cosine of pi over 2 plus I sine pi over 2. That's multiplying the pi over 12 times 6. And this is our polar answer. Now to go rectangular or standard form, we just have to know the cosine of pi over 2 is 0, plus the sine of pi over 2 is 1. So 1 times I is I, multiplied by the 1 over 64. Here I'm running out of room. And we will get 1 over 64I would be the answer in standard form. Or you might want to put 0 plus 1 over 64I, but of course 0 plus anything is itself. All right, for our next DeMoivre's theorem example, what if they give you a number that's not in polar form? They put this one, the square root of 3 minus I raised to the 6th power. So what we're going to have to do is one more example where we have to change from the standard or rectangular form to polar form. So I'm going to go ahead and say that R would equal the square root of a square plus b square. So we're just going to take this square root of 3 minus I and change it to polar form. So that would make R equal the square root of 3 is a. We're going to square that. So that's kind of nice because it's going to undo this. The b number is -1 there, so we're going to say that is plus -1 squared. So R would equal the square root of 3 squared is 3 plus 1, and very nicely R comes out to be the square root of 4, which will give us 2. Now, the angle we need, we're going to say, well, to get that, we got to take the tangent of theta and say that that is equal to b over a. Now, b is -1, a is the square root of 3, and some of you are probably thinking it's going to come out a -30 or a -60 degrees here. So you know what I want you to do? Go ahead on your calculator real quick. And we'll go ahead and put this in degree mode. We'll say to get the angle, take the inverse tangent of both sides. And some of you already know which one this is, but I'll pause and let you do it real quick. All right, so you should have got -30 degrees in there. Now be careful because remember, this is the real axis. This is the imaginary axis. And this point, if you were to plot it, the square root of 3 -1I would be here in the 4th quadrant. So your calculator gave you this angle, and you want to now add 360 to that in order to get that 4th quadrant angle we're looking for. So now we're at 330 degrees. So let's just go up here and rewrite this problem, because in polar form, this is going to work so much nicer. We're going to say in polar form, the square root of 3 minus I is 2 times the cosine of 330 degrees plus I sine 330 degrees. And now we are going to take this and raise it using DeMoivre's theorem to the 6th power, like we have the other example. So if it's not in polar form, get it in polar form first. All right, so now we can say that 2 gets raised to this power out here of 6 times the cosine of 330 degrees gets multiplied by the 6, that n number, and then the sine, same thing here. So we got 330 degrees times 6. Now, of course, we're going to get a angle greater than 360, so we're going to have to also adjust that. All right, so All right, so I went ahead and I multiplied the 2 to the 6th power, got 64. 330 degrees times 6 is 1,980 degrees. So I just kept subtracting 360, subtracting 360, subtracting 360 until I got within 0 to 360. So this is the answer they're looking for in polar form here. So we'll go ahead and note this. And again, we want to go ahead and change from polar to rectangular form. So we know the cosine of 180 degrees is -1. The sine of 180 degrees is 0. So in this case, we're going to end up with 64 times -1, and we are going to get -64, and the eyes will go out. So the famous Abraham DeMoivre, and that would just have worked as well if that was a 60, a power of 6,600. You could easily multiply those together. So great job by him. All right, now if there is a way to write complex numbers and raise them to higher powers, this is a way to go ahead and find the nth roots of complex numbers. So, for example, we might want to take the square root, the cube root, the fourth root, the fifth roots, and so forth of complex numbers. So notice it says here, this is the nth roots formula for a positive integer n. The complex number z equals r times cosine theta plus I sine theta has exactly n distinct nth roots given by, and some of these formulas can look intimidating, the nth root of r times cosine theta plus 2 pi kn plus I sine that. I'll call it ditto. Or you could also take 2 pi and write it in degrees as 360 and rewrite this formula. Now here's the catch here where this k number in this formula starts out 0, 1, 2, and it goes to 1 before the square roots. All right, so I guess the best way to show you both the, how to work these type problems is to go ahead and we'll just do one down here. All right, so it says find the complex square roots of this complex number in polar form, 9 times the cosine of 30 degrees plus I sine 30 degrees. Now, if they want the square roots here, we're going to have to identify some numbers here. N would be 2. All right, so if it was cube roots, n would be 3. Fourth roots, n would be 4. Now notice k here starts at 0. If n is 2 and goes 0, 1, and stops. It's always 1 less than whatever the n number was. So for example, if this was a cube root, k would be 0, 1, 2. If this were a fourth root, k would be 0, 1, 2, 3, and so forth. Okay. Now, the rest of these things, I don't think it's hard to find. Now, if we're after r here, I mean, you can see the r or modulus value is going to be 9. So we'll come down here and put that. And the angle theta, no doubt, is 30 degrees to start out. So these are the things you want to get in the nth root formula. Now to get your square roots of this complex number, here's how to proceed. We're going to use the formula here on the right because this one's degrees, and we will do one, of course, in radians with another example just to make sure you have it here. So we're going to come over here and put when k equals 0, okay, we're going to have the nth root of r. So again, I'm looking up here, we're going to say that is the square root of 9. All right, so let's go ahead and put this times the cosine of 30 degrees plus 360 degrees times k is 0, all over n is 2. And then we can put plus I sine. A lot of students will put dittos here, but I'll go ahead and write that out. So this will always be the same over here. And then this is your first of 2 square roots of this complex number. So the square root of 9 is 3 times the cosine of 30 degrees plus 0, 360 times 0 is 30, divided by 2 would be 15 degrees plus I sine 15 degrees. So this is one answer. So if they're after square roots, you're going to have 2 answers, cube roots 3 answers, fourth roots 4 answers, and so forth. All right, so let's go ahead and keep going here. So when k is 1, this will give us the second of our roots here. We're going to say this formula up top is still going to hold. We're going to take the nth root of r and go ahead and just keep going here. So it's very similar in ways. So we're going to say it's the square root of 9 times the cosine of 30 degrees plus 360 degrees times 1. So k is 1 in this case, all over 2. And then plus I sine that. So we're going to just go ahead. Now you might get tired of doing this. You may want to just put dittos here, because whatever this angle is going to be 2. All right, and then we will say the second of our 2 square root answers is going to be 3 times 360 plus 30 is 390. 390 divided by 2 is 195, and then plus I sine 195. All right, so not only can we raise complex numbers to higher powers, we can also take the roots of complex numbers by using this nth root formula. Oops, I was going to circle these and say, so these are my 2 nth root answers right here. This is what you would put. My writing tablet's a little bit slidey today. All right, so in this example here, we're going to use this nth roots formula again to find the complex fourth roots of this number, 81 cosine 4 pi over 3 plus I sine 4 pi over 3. So we're going to write these fourth roots using both polar and rectangular form, and then we're actually going to graph them as well. All right, so let's start out here. So if we're after the fourth roots now, remember, let's go ahead and identify some of our parts of this problem. We're going to say n is 4, so we're after fourth roots. K would equal 0, 1, 2, 3. So if you didn't get it that first example, hopefully you'll see it a little better here. So it goes up to 4 starting at 0, so you'll have 4 answers. All right, and then what else do we need? We need the modulus r here is 81, and the argument or angle would be 4 pi over 3. So it's always a good idea to get your ducks in a row here, and then we'll come down and go ahead and start the process here. So when k is 0, we're going to get the fourth root of 81. All right, so we're using this formula now in radians up here. Okay, so, and we're going to multiply that by the cosine of the angle, 4 pi over 3 plus 2 times pi times 0, all over, now that's a bad 3 there, let me fix that, all over 4. And then I am going to get lazy on this one and show you what I mean. I'm going to put I sine ditto, so all of this is over here. Young, that's just freaking lazy. It is. All right, so what is the fourth root of 81? All right, it is going to be a nice 3 there, times the cosine of, and we can say 4 pi over 3, and this is going to be 0, divided by 4 is going to be 4 pi over 12. So this first angle is going to be pi over 3, this first of 4 fourth roots, plus I sine pi over 3. Okay, so there's the first answer in polar form. All right, when k equals 1, I'm going to go ahead and stop the video and come back here. I'll run through this one more time with y'all, and I'll stop to save some video here because this is just going to chew up a lot of time here. It'd be 4 pi over 3 plus, when k is 1, 2 times pi times 1 all over 4. And I'll put plus I sine ditto is also, this is the second of the fourth roots, 3 times the cosine of All right, so on this one we got 4 pi over 3. Now 2 pi over 1, 2 pi times 1 is 2 pi over 1 is 6 pi over 3. So what we would get here is 10 pi over 3, okay, divided by 4 is 10 pi over 12. So this would give us 5 pi over 6 plus I sine 5 pi over 6. Now we could put in k is 2 and k is 3, but there is a little trick I could show y'all on this. And on these higher powered ones, these angles right in here are always going to be equidistant. All right, I don't care what the higher power is. This is a little trick. I don't know if a lot of instructors would show you this, but let's say this is, if we changed it to 6, 2 pi over 6 radians right here, right? It would be pi over 3. So there is a difference of, if you go 5 pi over 6 minus 2 pi over 6, each one of these will increase by an angle of 3 pi over 6 radians. All right. Now, if you don't believe me, I'm going to keep going here and show you. All right. Now, here's a shortcut if you see it. Now, if you don't, you could put k equals 2 in here and then put 2 in there and keep doing it. But I'm going to tell you right now. All right, so when k is 2, I change colors here. It's going to be 3 times the cosine of, so notice there was a difference of 3 pi over 6 here. So if I keep doing that, if I go 3 pi over 6 plus 5 pi over 6, this will be 8 pi over 6, or 4 pi over 3 plus I sine 4 pi over 3, right? So this is kind of a trick here, a quick trick. And then finally, if I go when k is 3, and this will be my fourth answer, my fourth of the fourth root answers, this is the shortcut, equals 3 times the cosine of 4 pi over 3 plus 3 pi over 6. So this would be 8 pi over 6 plus 3 pi over 6. You would get 11 pi over 6. So these angles are going to be equidistant apart, plus I times the sine of 11 pi over 6. All right, so all of these 4 of the fourth roots here are in polar form. Now I'm going to put them in rectangular form and graph them on my calculator, okay? So I want y'all to do it as well. And let's round these just 1 decimal place, okay? So I want you to go ahead and go into radian mode and put this from polar to rectangular or standard form for me. And I'll come back and we'll see if you have it. All right, so I went ahead and I found in standard or rectangular form, here are the 4 complex fourth roots of this complex number in polar form. All right, so we have the 4 fourth roots in polar form and the 4 fourth roots in rectangular form. I hope that you all arrived at these answers as well. All right, so we're going to go ahead and graph those fourth roots real quick here and show you what it looks like. All right, so the first of the 4 answers, the fourth roots we found, was 1.5, or we could have said 3/2, and we could have also written that using unit circle values, but we'll put 1.5, 2.6 here. All right, and remember, this is the real axis, and this is the imaginary axis. All right, the next point was negative 2.6 here on the real axis. 1.5, about halfway would be there. Negative 1.5, negative 2.6 would be down here. And then 2.6 and then negative 1.5. About right there. And then what a lot of textbooks will do is they'll go ahead and put these R values here out to each of the complex fourth roots. And then they'll actually put this in a circle. They'll go ahead and put a circle around it when they graph these. And that will be the conclusion for our lesson on complex numbers in polar form. All right, Bob Young signing off. Las Vegas Raider hat, just win, baby. I want you guys to do that on the homework and the test. Bye.